Okay, so good afternoon. My name is Jakub Černý. I'm from Czech Technical University in Prague, and I would like to talk about the work of me, Boýanský, and Kiekintveld on a domain-independent incremental strategy generation algorithm for computing Stackelberg Equilibria in extensive form games. So first, please let me just briefly describe the framework we are working with. We represent games using a structure called extensive form, and extensive form is a model of sequential interactions between multiple decision makers. And this structure can be visually represented as a game tree in which every node corresponds to a unique game state of the game, and edges correspond to actions which transform one game state into another. In every game state, only one player acts, and all actions are deterministic so that they are always correctly executed, but we can also model imperfections by introducing stochastic nodes. This model also models imperfect observations by grouping certain nodes together into information sets such that the player cannot distinguish between nodes in the same information set. And the strategy in this model is hence one probability distribution over actions in every situation a player can face. And the solution of the model is then tuple of one strategy for every player such that no player has an intention to deviate. As always, we call these tuples equilibria, and there might exist different kinds of equilibria based what does it mean to do not have an intention to deviate. And in this work, we focused on computing an equilibrium called strong Stackelberg equilibrium in two-player games with general sum utilities. And the roles of the players in this equilibrium are asymmetric, such that we have one player called the leader who has a power to commit to a strategy, and a second player called the follower observes this strategy and then plays the best response. A problem of finding an optimal strategy for the leader to commit to is known to be an NP-hard problem, and hence no efficient algorithm is possible, at least if P is not equal to NP. But finding such strategies are a cornerstone of model applications of game theory because they can be used for many real-world settings. Because, for example, a leader can correspond to a market leader who has a power to set prices for items or services. It can be a defense agency committing to security protocol for protecting critical facilities, or it can be a cybersecurity software trying to secure data on servers in network infrastructures. And the main result of our work is that we do not need to consider the whole strategy space in order to compute the strong Stackelberg equilibrium. So consider the following example of an extensive form game, which is motivated by the last example I mentioned with the cybersecurity software. This game is called a Flip It game, and it is a game in which two players compete over resources in network infrastructures. And we have an attacker who can attack servers, and these attacks may or may not be immediately detected by the defender. The defender can also take actions in order to restore control of a given server. At the beginning, all servers are controlled by the defender, and it is called a Flip It game because the actions are called flipping actions. And in a simultaneous round, every player decides which node to flip. And the flipping action is successful when two conditions are met. First, the owner of the server does not flip it. And second, the player has to have a control of at least one predecessor of the server. And with each server, we have an associated reward and an associated cost. And for each flipping action, the players have to pay the cost. After every round, they collect their rewards as sums of rewards from all servers they control. So here you can see an example with two servers. We have server 0 with reward 2 and cost 3, and server 1 with reward 3 and cost 4. And at the beginning of the game, the attacker chooses whether to attack server 0, to attack server 1, or whether to pass. But he knows that after his action, the defender will also take an action. But because the defender is unaware which of the servers were attacked or whether the attacker passed, all of the game states of the defender are in the same information set. So let's say that the attacker attacks server 1, and then the defender passes. So after the first round, the server 1 is infected by the attacker. And in the second round, the attacker might try to attack server 0, and in the case it is defended by the defender, it remains uninfected. And now if the game has only 2 rounds, the players are now given utilities. And in the same way, we can evaluate any combination of sequences of actions. And the goal is to find an optimal strategy for the defender in this game. And this strategy is described by a strong Stackelberg equilibrium.
How is the payoff decided?
Yeah, the payoff is accumulated from the rewards which are given to the players after each round. And we subtract the costs for the flipping actions. Is that clear?
Cost -1 is for attacker, 1 is for...
The costs are the same for both players. So,
-1, 1.
yeah, sorry. The -1 is for the defender, and 1 is for the attacker, because the attacker was successful when attacking the server 1. Okay, so, but because this concept is NP-hard, it can be intractable to compute these kinds of equilibria even for small games. Because, for example, a simple flip-it game with a simple network topology with only 4 servers and 5 rounds has more than 10 million game states. And we tried to cope with this problem by creating a first algorithm which is able to compute strong Stackelberg equilibrium by incremental generation of a game tree. And because we would like to also scale to larger games, we present also a heuristic version of our algorithm. And the algorithm works in the following way. First, it creates a simple initial restricted game, and it computes a Stackelberg in this restricted game. And based on the solution, we expand some parts of the restricted game, and we repeat these steps until we reach an equilibrium. And the algorithm is guaranteed to converge to a strong Stackelberg because of the 3 key properties of the algorithm. First, we can represent every subtree rooted in a state of the leader by a generalized temporary leaf structure, which consists of the upper convex hull of leaves in this subtree. Second, the restricted games are always closed on the information sets of the follower, which means that whenever a state of the follower is inside a restricted game, every other state which belongs to the same information set is also part of the restricted game. And finally, we have a simple termination criterion which says that when no temporary leaf structure is reachable by the current strategy of the leader in the restricted game, we reach the strong Stackelberg in the whole game. So here you can see an example of an extensive form game on which I would like to demonstrate the steps of the algorithm. So first we take all the leaves and we find the upper convex hull of the leaves. And then we create the first restricted game, which is simply a state of the leader below which we append the leaves from the upper convex hull. And we compute the first strong Stackelberg, which is simply an action which leads to the state, to the leaf with the highest utility of the leader. Now we expand the restricted game, and we have 4 new temporary leaf structures. And again, we compute the Stackelberg in this game. And because the leader moves right in his upper game state, we have to expand both of the temporary leaf structures in the right branch, because there might be possibly reached by a leader strategy. So we do it, and note that we also expanded one of the temporary leaf structures in the left branch, because the algorithm has to ensure that the restricted game is closed on the information sets of the follower. I hope it is clear. So now we compute against strong Stackelberg, and because no temporary leaf structure is now reachable, we terminate the algorithm. Okay, so because we would like to scale to even larger games, we present this heuristic version. And first thing we do is that we drop the requirement for the restricted game to be closed on the information sets of the follower. And we know that if we do that, we lose the guarantee to converge to strong Stackelberg. And in our paper, you can find an example of an extensive form game in which the algorithm does not converge. Second, we approximate the upper convex hulls such that they contain a lower number of sleeves in order for the restricted games to be smaller. And also, we penalize the leader's utilities in the temporary leaf structures in order for the algorithm to do not take actions leading to the temporary leaf structures if possible, hence terminating in a lower number of iterations. And the parameter for penalization is epsilon, which will be used in the experiments. So for the experiments, we built our incremental strategy generation algorithm on top of the current state-of-the-art algorithm for computing Stackelberg in extensive form games by Černý and Boýanský. And we performed experiments with the domain I already mentioned, the flipped games. And we considered two versions of the flipped games based on the information which was provided to the players. In the first version, called the all points version, the players learn after every round the total sum of points they currently have. And in the second version, called the no info version, no information is given to the players. And we consider different topology structures, different network topologies, which you can see here. And we computed an equilibrium in games with more than 10 million game states. So here you can see the results achieved with our algorithm on the all points version of the flipped game. In the left graph, you can see the final sizes of linear programs describing strong Stackelberg. In the x-axis, there is a penalization parameter epsilon, and on the y-axis is the final LP size ratio, which is calculated as a number of non-zero coefficients in the linear program describing strong Stackelberg in the final restricted game divided by a number of non-zero coefficients in the linear program in Černý's algorithm. And we can see that for all values of epsilon, the LP sizes are less than 8 times smaller when compared with the full linear program. And in the right graph are the runtimes. Again, in the x-axis is the penalization parameter, while on the y-axis is the runtime ratio, which was again computed as the runtime of the heuristic algorithm divided by runtime of Černý's algorithm. And in the table below are depicted the deviations from strong Stackelberg, from the optimal utility given to the leader. And this deviation is calculated as an absolute difference between the value returned by the heuristic algorithm and the value of the strong Stackelberg. And even for the smallest LP, which is for graph 4C, here, which is about 2.8% of the original linear program, the deviation is only about 6.48% first. And here are the results in the no information version of the flipped game. Interestingly, it seems that the more complex structure of the graph 4C slows down the convergence of the heuristic algorithm. We think this is because the information sets are larger, and also the upper convex hulls are larger and contain pretty similar leaves, and hence the algorithm expands only a few temporal leaf structures in every iteration, and it needs more iterations to converge. But still, the sizes of the final linear programs are pretty small, even for smaller values of the parameter epsilon. And also, the deviations are small. They are lower than 3% from the, well, when compared with the value of the strong Stackelberg, even for larger parameters, for larger values of parameter epsilon. Okay, so this is all I wanted to show you. So thank you.
We have enough time for questions.
Great.
So you said in the flipped game,
Mm-hmm.
If the attacker and defender pick the same server, then the server does not get flipped.
Yeah, well, if they flip the server, it will remain under control of the player who had the control in the previous round.
I see, so it's symmetric, yeah.
Yes.
Mm-hmm. But in that case, what is there anything special about who gets chosen to be the defender and who gets chosen to be the attacker, apart from who owns the servers in the beginning? It seems like you have a subtree where everything is flipped.
No, I think like this was motivated by the scenario because this work was funded by the Army Research Lab, and they were interested in these scenarios. So leader in this case is the defender, because we assume that the attacker is able to somehow check what might be the strategy of the defender in the network by like checking the site and perhaps finding how often the actions are performed by the defender, like changing the passwords and these kind of things. So in this scenario, we assume that the defender is the leader in the strong Stackelberg equilibrium.
In the beginning, at least.
Yeah, at the beginning. Sorry. So.
I mean, what I'm wondering about is, so you have some subtree there where the attacker successfully flipped all the servers.
Mm-hmm, yes.
And then in that subtree, you have the same game, but with the rules exchanged, basically.
Sorry, still don't understand this. So can we take it offline? Like, yeah. I guess.
I have two questions on the details of the algorithm.
Uh-huh.
So the first one is that every time you expand the game model within the algorithm, do you start the LP from scratch, or is there some sort of odds type?
No, we try to reuse the LP from the previous iteration and change only those constraints which are affected by this expansion.
Okay. And then the second thing is that when you do the approximation of the convex hull, do you use an inner approximation, or you don't constrain it to be an inner approximation? It could be inner or outer or a little bit of both.
Yeah, it can be anything. We do not constrain it. Okay.
Could you talk a little bit about the role of correlated equilibrium or correlated strategies?
Yes, because well, I didn't want to go into details for this like short talk, but yes, because the branch and bound algorithm on top of which is the iterative constraint generation or the strategy generation build is done by, well, we consider the correlated version of the Stackelberg so that we compute strong correlated Stackelberg, and we try to well, because it is an upper bound on Stackelberg, we try to find like how to constrain this linear program so that it produces a pure best response of the follower. And hence, all the graphs also were for linear programs because they are linear programs. And because, well, this strategy generation can be done even for the MILPs, but we just went for the correlated version because of the scalability. Okay.
So about Tom's question, the LP, so you restart the LP for the next LP, you start from the solution of the previous LP?
Well, we use CPlex.
Oh.
And Cplex has some magic inside which is able to do that. So we try to reuse the models.
Okay.
So we take the model from the previous iteration, update all the constraints which are necessary to be updated, and then we try to resolve it.
So
Okay.
but when you add some constraints,
Mhm.
so you don't get a hot start in the primal, so are you actually using dual simplex to get a hot start in the dual? Is that what you
We tried different methods for solving. We didn't go much into what should be the best thing. We just measured times of the Cplex, and we realized that actually the barrier methods were the best and performed the best in this setting.
But they don't get a hot start though.
No, I don't. I'm not sure what is the current implementation in Cplex. Sorry. So
Let's thank all the speakers again.
thank you.